Good afternoon, everyone. So now we understand how to calculate probability of a single sample space. If there are many events defined in a single sample space, we can calculate probability. Probability in the first topic, we simply understood basic terms. In the second topic, we understood about set theory. And in the third topic, finally, we are calculating probability. As far as calculating probability is concerned, so we are simply now able to determine probability. In this topic, we started with 3 axioms of probability. So tell me, what is the very first axiom? Okay, tell me what is the meaning of axiom?
Believe.
Belief.
Sir. Belief.
It's a belief. Just like the belief that ahimsa paramo dharma. Just like the belief that God is there. Just like the belief that any such belief that cannot be proven. Just like the belief that mass of the universe is conserved. Just like the belief that energy of the universe is conserved. So what is the first axiom?
Probability of
Probability
event
of
greater than
any-
0, greater than equal to 0.
Probability of any event is greater than or equal to 0. That means, which means what?
It
That
will
you
not
can
be
never have
non-negative.
non-negative, exactly. So you cannot have negative chances of occurring of any event. If an event is there, worst case, it will have 0 chance of occurrence. Worst case, it will not take place. If the event will not take place, it has 0 chances. You can never have negative chances. What is the second axiom of probability?
Probability
Probability
of
of a sample space is equal to 1.
Probability of total sample space is always equal to 1. So what is the meaning of this? What is the meaning of this? Probability of whole sample space equal to 1. What is the meaning of this? What do we mean by writing this?
Probability of
Let's-
sample space is always 100%.
Something will happen.
Yes.
In whole sample space, if we are covering all possibilities, something will happen. Isn't it? And what is the third axiom? Third axiom is that probability of union of 2 events will be equal to simply the sum of their probabilities. But this axiom has a condition. So what is that condition?
Mutually
A and B are
exclusive
mutually
events, sir.
exclusive.
A and B are mutually exclusive events. So what do you mean by mutually exclusive?
one will occur, other is
They do not occur simultaneously.
They cannot occur simultaneously. If one will occur, then it's definite, then other cannot occur. For example, getting 1 on a dice and getting 6 on a dice are mutually exclusive events. Because if you roll the dice, you get 1, then you don't get 6. And if you get 6, then you don't get 1. So these are the 3 axioms of probability. And then second thing we did, the second thing was finite sample space. In the finite sample space, finite sample space with equally likely outcomes. So finite sample space with equally likely outcomes. There is a finite sample space with equally likely outcomes. Let random experiment, if in language we write it, it seems complicated, but still we will write it. If random experiment eta has sample space S with capital N number of equally likely outcomes, capital N number of equally likely outcomes, then probability of each outcome will be how much?
1 by n, sir.
1 by n, sir.
1 by n. Probability of each outcome would be small p is equal to there be an event A defined on sample space S such that event A contains a small n number of outcomes, then the probability of event A will be what?
So small n
Small
by
n by
by n,
capital
sir.
N.
Small n upon capital N. We say a small n number of outcomes are favorable to that event, and capital N number of outcomes represent total possibility of outcomes in whole sample space. So favorable outcomes divided by total outcomes. Don't go by the complexity of the language here. Random experiment is there, and that random experiment has got a sample space with n number of equally likely outcomes. Then each outcome will have same chance of occurrence, and that chance of occurrence will be 1 upon capital N. Now you can define, in a sample space, there are multiple ways in which an event can be defined. So let there be an event capital A defined on that sample space such that event capital A contains a small n number of outcomes. Then probability of this event will simply be 1 upon capital N, 1 upon capital N, 1 upon capital N, 1 upon capital N, small n number of times. Okay. So we can take an example here. We can just write like in this whole rule, in this whole theorem, random experiment could be rolling a die. Random experiment could be rolling a die. Then what will be the associated sample space? This associated sample space with this random experiment. What is the S then?
1, 2,
S
3, 4,
is
5, 6, sir.
1, 2, 3, 4, 5, 6. Then probability of getting 1 or probability of getting 2 or probability of getting 3 or probability of getting 4 or probability of getting 5 or probability of getting 6. All of them are equal to 1 upon capital N. And capital N value is 6. So that becomes 1 upon 6. Now, in this sample space, we can define multiple events. like getting an even number, getting an odd number, getting a number greater than 2, getting a number less than 5, getting a number which is a prime number, getting a number divisible by 3, getting a number divisible by 2. There are so many ways an event can be defined in the same sample space. So event could be, one example of event could be getting an even number. One example of event could be getting an even number. So getting an even number, how many favorable outcomes are there? 2, 4, 6. That means small n becomes 3. So what is going to be the probability of this event capital A? The probability of this event capital A will be 1/2. So the rule is very simple. If a random experiment eta has a sample space S having n equally likely outcomes, then the probability of each such outcome will be 1/N. Now let there be an event capital A defined on the same sample space, such that that event contains n small n number of outcomes, then probability of that event A will be small n upon capital N. And this is not a fundamental definition of probability. No, fundamental definition of probability is chance. That's it. Probability, what is the fundamental definition of probability? Fundamental definition of probability is chance of occurrence of something. Fundamental definition of probability is chance of occurrence of something. That is the fundamental definition. This favorable upon total is not the fundamental definition. This can be done only in case of finite sample spaces. Okay. One thing is very clear, that this formula we have obtained using 3 axioms only. This formula, small n upon capital N, we obtained using our 3 axioms. The next thing was law of addition of probability. Addition law of probability. So what is addition law of probability? Addition law of probability is this was the next thing we did. The third thing, addition law of probability, and addition law of probability is what? That probability of A union B will be probability of A plus probability of B minus probability of A intersection B. You remember we defined inclusion-exclusion principle even for 3 sets. I hope you remember. We defined inclusion-exclusion principle for 3 sets: A union B union C. Number of elements contained in A union B union C is equal to number of elements in A, and then number of elements in set B, and then number of elements in set C, then number of elements in A intersection B, then number of elements in B intersection C. Also subtract number of elements in C intersection A, but finally add number of elements in A intersection B intersection C. Cool. Now, just like we did with 2 sets, similarly, if I divide this whole thing by capital N, A union B union C, number of elements in A union B union C is equal to number of elements in event set A, number of elements in set B, number of elements in set C, minus number of elements in common elements of A and B, minus common elements in B and C, minus common elements in C and A, plus common elements, the whole common elements in all A, B, and C. This last one is not minus, this last one is plus. Now divide every term by capital N, 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 by capital N. Then now what is this ratio of small n upon capital N representing? The ratio of small n upon capital N is representing what? This is representing probability. So probability of A union B union C is equal to probability of A alone plus probability of B alone plus probability of C alone minus probability of A and B simultaneously occurring minus probability of B and C simultaneously occurring minus probability of C and A simultaneously occurring plus probability of A, B, and C simultaneously occurring. For two events defined in a sample space, this is additional law of probability. For two events defined in a sample space, this is additional law of probability. And for three events defined in a sample space, this is the additional law of probability. If you are defining three events, A, B, and C, in the same sample space, the additional law of probability is a little big, but since we have proved this inclusion-exclusion principle in set theory, for us, it is not a challenging thing. For us, it is simply dividing by capital N, dividing by capital N, dividing by capital N, dividing by capital N, dividing by capital N. Once we divide by capital N, then we get the corresponding probability values. Then we get the corresponding probability values. Now is the time to solve some. Now is the time to attack some questions based on additional law of probability. So let's go ahead and attack some questions. You tell me what is the score? Tell me what is the score, people?
7, sir.
So we are now going to solve some very interesting problems. As a seventh problem, let's say in a society, we have 150 households. There are 150 households, and out of 150 households, 20 households, 20 families have dog as pet, and 18 have cat as pet. Have cat as pet, and whereas 5 have both dog and cat as pet. Find out the probability of find out the probability of a household probability of a household having pet. If in that society, if I randomly pick a family, what is the probability that that family will have a pet? If I randomly pick a household in that society, what is the probability that that household will have a pet? Okay, so how my event is satisfied? The day you will be able to translate the probability requirement into some kind of union intersection, then you will be able to tackle, you will be able to attack probability questions very easily. You will be able to attack probability questions very easily if you can translate the probability question given in the language in terms of union intersection kind of things. So probability of having a pet means what? In terms of union intersection, in terms of sets, probability of having a pet means what? Probability of having a pet means having a dog as pet or cat as pet. If a household is having dog as pet, then also he satisfies my event. If a household is having cat as pet, then also that household satisfies my event. All I want is that family is having pet. If a family is if a family is having pet, that family satisfies my event. So if that family is having dog as pet, then also that family satisfies my requirement. He has a pet. And if that family has cat as pet, then also that family is satisfying my requirement of having a pet. Or there is one more way. If a family has both dog and cat as pet, then also that family satisfies my event. So my event is whether a family is having a pet or not. If a family is having dog as pet, then also my event is satisfied. If a family is having cat as pet, then also my event is satisfied. If a family is having both as pet, then also my event is satisfied. Now you tell me, what is this representing? If having a dog is event A and having a cat is event B, then
Union, sir.
Union, sir.
union, exactly. If having a dog is event A and having a cat is event B, then this is very clearly representing A union B. This is very clearly representing A union B. And then we know, my dear friends, from addition law of probability, that A union B can be written as probability of A alone plus probability of B alone minus probability of co-occurrence of A and B. Now, probability of A alone is 20 divided by 150 because 20 families have dog. Probability of cat alone is having 18 upon 150. And then there are families which own both, which have both dog and cat as pet. If they have both dog and cat as pet, then we are going to get such cases 5 out of 150. We are going to get final answer here, and that final answer is how much? 20 plus 18 minus 5 divided by 150, which is 0.22. 22% chances are that a random family, if I ask a random family that whether you have a pet or not, then 22% chances are that that family is going to say, yes, we have a pet. 22% chances are that if I ask a random family whether you have pet or not, then 22% chances are that the family will reply, yes, we have pets. Now this becomes a little confusing. Answer seems like 20 upon 150, having dog, also satisfying, and 18 upon 150 also satisfying us, and 5 upon 150 also satisfying us. So one answer seems like, it seems like as if we have 43 upon 150 as the answer. It seems like the answer could have been 28.67%. So why the hell the answer is 22%, and why the hell the answer is not 28.67%? If we simply add favorable elements, it's actually 43. If we simply add 20 have dog, 18 have pet, and 5 have dog and pet both. So if we simply add all of them, it comes out as 43. So why the hell the answer is not 28.67%? Why the hell the answer is 22%? The answer, the logic, the intuition, why this is happening, the intuition can be given by Venn diagram. So let us understand that why is this happening? Why 28.67% is a wrong answer, and why 22% is the correct answer? Why this one is right answer and why this one is wrong answer? Yes, this one is a wrong answer. Okay, why? Let us go into the Venn diagram, and then we will be able to understand that why is this happening. You see, some families have, there are total 150 families, so whole sample space is representing 150. Whole sample space contains 150 elements. Out of those 150, there are few families, only 20 families having dog as pet. And then there are 18 families having cat as pet. Then there are 18 families having cat as pet. I told you, whenever you do such problems using Venn diagram, always start at the center. So five families have both A and B. 5 families have both dog and cat. Now, out of 20 dogs, 5 have already been covered. So how many are remaining? 15. How many are remaining? Naturally, 15. And out of 18 families having cat, 5 have already been covered by this common area. So how many are still left out of 18? Out of 18 families having pet, 5 are covered in this common area. So how many are remaining? Remaining are 13. Now, Venn diagram makes the picture so clear, in no confusion. Venn diagram makes it so crystal clear in such an easy way. So now you simply add them together. 15, 5, 13 total favorable cases upon 150. And you are going to get 20 plus, you are going to get 20, 15 plus 5, 20 plus 13 becomes 33, 33 upon 150, and you get the right answer, which is 0.22, which is 22%. Now, in the same kind of problem, sometimes they might ask, what is the probability of having no pet? What is the probability of having no pet? So there is a mathematical way, and then there is a Venn diagram. Mathematical way is little complicated. Venn diagram is much easier. Venn diagram can solve such problems in just one line. Venn diagram can solve it just like that. That your mathematical way of solving problem will hide in the corner. Yes? So that's such an easy thing if you approach the same problem using Venn diagram. So let's go ahead and repeat the same problem actually. Now we are going to repeat the same problem, but this time suppose I'm going to ask you little different question in the same sample space. In the same sample space, I ask you a little different question as an 8th problem. This time you calculate the probability of a family or a household having no pet. Probability of a household having no pet. Now, mathematically, you can approach this problem like if A is defining the event of having dog as pet and B is defining the event of having cat as pet, A is defining the event of having dog as pet and B is defining the event of having cat as pet, then naturally we are interested in no dog and no cat because I don't want the family to have a pet. Suppose I ask the family, and what is the chance that the family is having no pet? So naturally, we are interested in no dog and no cat also. And I am interested in the simultaneous occurrence of both. If no dog, but cat is there, I'm not satisfied. If no cat, but dog is there, I'm not again satisfied. If both dog and cat are there, then also I'm not satisfied. I want strictly no dog and also I want no cat. And you tell me, that's what you will become a master of probability the day you can translate any probability question into an and problem, ya fir an or problem. If you can translate any probability question into an and problem, otherwise an or problem, then you will become 50% your problem is solved at the very first step. If you can translate the given problem into an and problem, otherwise an or problem. So this is an and problem. I want no dog, I want no cat. Now you tell me, A defines the event of having dog as pet and B defines the event of having cat as pet. Then no dog will be represented as what? If A defines the event of having dog as pet and B defines the event of having cat as pet. Let me write it. A defines the event of having dog as pet, event of having dog as pet, and B defines the event of having cat as pet. Then no dog will naturally be represented as A complement. And what do I write in between? And no cat will be represented by B complement. What do I write in between?
Intersections.
Intersection, because I want simultaneous occurrence of both these events. I want simultaneous occurrence of both these events, so I write intersection. Then, my dear friends, use De Morgan's law. De Morgan's law is what? De Morgan's law says that intersection of complements is going to be equal to complement of unions. Complement of unions. Now, probability of complement of any event can always be written as probability of 1 minus probability of that event. Probability of complement of any event can be written as 1 minus probability of that event. Now, my dear friends, P A union B can be broken further, just like previous problem. A union B can be broken as PA plus PB PA plus PB minus PA intersection B. Now we are going to get this as 20 upon 150, having dog as pet, 18 upon 150 having cat as pet, and 5 upon 150 having both dog and cat as pet. So naturally we are going to get 1 minus 0.22. No, don't think that. If you think this problem by keeping in mind the solution of previous problem, then of course you will think that why we are doing all this. We would have answered simply as 22% was the probability of having pet. So 78% will become probability of not having a pet. Of course, that was straightforward. But treat this problem as an independent problem. Treat this problem as a standalone problem. Don't think that we solved previous problem. Okay? If you did not solve previous problem, then you would have gone like this from basics. So from basics you start and it becomes 0.78. Using Venn diagram, it becomes much easier. If you use Venn diagram, it becomes actually very easy, that there is event A is containing 20, event B is containing 18, event A is containing 20, event B is containing 18, and always start with the centermost. Always start with the centermost. So 20 are there, 5 already covered, we have 15 left, and 18 are there in cats. 18 families have cat as pet, 5 have already been filled here. So out of 18, out of total 18, how many are remaining? How many are remaining? If 5 is already considered, 13 is remaining. Now out of 150 total, how many are having neither dog nor cat as pet? I'm interested in this area. I'm interested in this area. This area is 150 minus this total thing. 15 plus 5 plus 13. $150 minus 33. This is how much? 150 minus 33, 117. So probability will be what? Probability will be Ruko. I will cure you permanently. Probability will be 117 are favorable, total are 150. Calculate probability. 117 are favorable, total is 150. You are going to get 0.78 again. So which one you like more? This analytical way or this diagrammatical way?
Venn diagram, sir.
Sir, Venn diagram, sir.
Huh? Venn diagram. Naturally, Venn diagram makes it very simple. Moving on to the next problem. So there is a party going on. There is a party going on, and in party there are 50 people. 50 persons are there. And out of these 50 persons, so there is this party going on. Weekend is there, na? Saturday. So there are 50 persons out there. Out of these 50 persons, my dear friends, out of these 50 people, 50 persons, 20 are wearing black shirt. 20 people are wearing black shirt and 10 people are wearing red shirt. And also, there are 12 people who are wearing green shoes. Green shoes. That's so weird, no? Weird as it might seem, but it's anyway a hypothetical situation, so take anything. Yes, so we have 20 black shirts and we have 10 red shirts. 20 people are wearing a black shirt, 10 people are wearing a red shirt, and 12 people are wearing green shoes. Now, it's also given that 8 people who are wearing black shirt, 8 people who are wearing black shirt are also having green shoes. And it's further given that 5 people who are wearing red shirt are also having green shoes. Now, if I pick a random person, blindfolded, I become blindfolded and I go in the party and select one random person. What is the probability that that person is wearing none of them? If I become blindfolded, and becoming blindfolded, I go to that party and just pick one person randomly. What is the probability that the person doesn't wear any of them? Probability of a person not wearing any of them. I want to find out the probability of a person not wearing any of these things. Neither a black shirt, nor a red shirt, nor green shoes. Cool. So this is the question that we are having. So how many total events have been defined here? In this given sample space of 50 outcomes,
5, sir.
How many events have been defined?
3, sir.
No. 3. One event is event A representing black shirt, event B representing a person wearing red shirt, and event C represents a person wearing green shoes. So let us define these events. Let event A defines the event of a person, event of a person wearing black shirt. Event of a person wearing black shirt. And let B is defining the event of a person wearing red shirt. In fact, let's name these events as capital B and capital R so that we know. B stands for black shirt and R stands for red shirt. And let event G is the event of a person, event capital G is the event of a person wearing green shoes. Event of a person wearing green shoes. Now, what I'm interested in? I'm interested in a person not wearing any of them. I'm interested in a person not wearing any of them. No black shirt, no red shirt, no green shoe, nothing, none of them. So basically, I'm interested in no red shirt, no black shirt, no black shirt, and now and is a very strong word here. And I'm interested in a person wearing no red shirt and again, and I'm interested in a person wearing no green shoe. So notice that I'm interested in no black shirt, but notice more on this word. And I'm interested in the person wearing no red shirt. And notice again that there is connection of and the person is wearing no green shoe. The person is wearing no black shirt and no red shirt and no green shoe. So no black shirt means what? No black shirt means complement of B. And means what? You tell me.
Intersection, sir.
And means intersection. Ramanujan Bose. Kaise ho? And no red shirt means what? The complement of event R. And means what? Again, and means simultaneous occurrence with the next event. And the next event is representing complement of green, complement of event G. Now, using De Morgan's law, I can write this as I'm interested in no black shirt means the complement of black shirt. I'm interested in no red shirt means the complement of red shirt. I'm interested in no green shoe means the complement of event G, event capital G. Now, using De Morgan's law, I can write this B complement intersection R complement intersection G complement as the complement of B union R union G. Using De Morgan's law says that the complement of unions is equal to the intersection of complements, isn't it? So we proved De Morgan's law earlier in set theory, and that De Morgan's law we are using. Now, the probability of complement of something is always going to be equal to 1 minus probability of something. If you are interested in probability of complement of a rock, then it will become equal to 1 minus probability of rock. If you are interested in probability of something complement, it will always become equal to 1 minus probability of that something. 1 minus probability of that something. So complement of something, it becomes 1 minus probability of that something. Like this. Okay. Now, this B union R union G. Black shirt union red shirt union green shoes. This can be written using additional law of probability. This can be written P of black shirt plus P of red shirt plus P of green shoes minus black and red simultaneous minus red and green simultaneous minus red and green simultaneous minus green and minus Black and red and green, black and green bacha. So green and red simultaneous. Finally, black and red and green, all three simultaneous. I have used additional law of probability here. I have used additional law of probability here. Now, probability of having a black shirt is simply 20 upon 50. Probability of wearing red shirt is simply 10 upon 50. Probability of wearing green shoe is simply 12 upon 50. Then nobody can be wearing black shirt also and red shirt also. That's a weird thing to do. You cannot have black and red both shirts being worn simultaneously. I mean, only a crazy person can do that, isn't it? Wearing a black shirt also and wearing a red shirt also. So that's not going to be a possibility in the current context. We believe that all these people partying together are same people, are people with common sense. Okay, so there is zero. But red shirt with green shoes, that can happen. Red shirt with green shoes, that can happen. And that value is given as 5. So there are 5 such people who have simultaneous occurrence of red shirt and green shoes. And then there are, I have written R here, I should have written B here. Then there are people wearing black shirt and green shoes together, and 8 such persons are there. 8 such persons are there. Last one, you tell me, last one will be what?
0, sir.
0, because no person can wear black shirt, red shirt, green shoe, everything. Basically, black shirt and red shirt cannot go together. Black shirt and red shirt, they cannot go together. So you calculate this, you are going to get the final answer. Calculate this, calculate this. Let's calculate this. We can use Venn diagram too. Probably, Ramanujan, you joined midway. Previous 2 problems we have done. Once using mathematical approach, analytical approach, and once using Venn diagram. I don't want just to feed one thing. I want both approaches must be mastered. Master analytical approach also, and then you master Venn diagram approach. Of course, in exam you are going to follow Venn diagram, but also this anything asked, once you have the ability of decoding it either as an AND problem, otherwise as an OR problem, it improves your it improves your ability to tackle probability questions with a lot of proficiency. So because you joined, except Ranbir Singh, no one is going to wear 2 shirts or more together. Exactly. So that's why I said that this is a party with sane people. This is a party with people having some common sense. Okay. So 20 plus 10.
0.42, sir.
12 minus 5 minus 8 and total divided by 50. 1 minus 0.58. 42%. 0.42. Now you see why axiom number 1 is a very strong belief. Because you don't ever find an evidence against it. You always get probability. No matter how you approach, you always get probability values less than 1. So this is 0.42. Okay. But as we have done with previous 2 problems, we are going to do it here again. That rather than using this analytical approach, if we would have used simply the Venn diagram, the problem could could have been tackled in just one line. If rather than using this whole lot of analytical approach, we could have solved it using Venn diagram. We could have solved it in just 2 lines. And how? Here is how. Here is how. So there are people wearing red shirt. There are out of 50 people in the party. So total sample space is representing how many elements? Total sample space is representing 50 elements. And out of these 50 elements, 20 are wearing black shirt. And then, my dear friends, there are people, 10 people wearing red shirt. Notice carefully that I have made no intersection between black shirt and red shirt. There is no intersecting area between black shirt and red shirt because they cannot occur simultaneously. Then there are people wearing green shoes. Then we have people wearing green shoes. Always start with common areas. For example, black and green common areas are 8. Just one little change I'm doing right now here. Number of people wearing green shoes is 15, let's say, because it can't be less than 13. And let us recalculate this. I have done one small change in the data of the problem. 20 plus 10 plus 15 minus 13 upon 50. So this is 0.64. %. So eight persons are belonging to both black shirt club and also the green shoes club. And then there are 5 people belonging to red shirt club and also the green shoes club. So there are 5 people belonging to common area of red shirt and green shoe. Now, total black are 20. Out of 28, you have already considered. Out of 20 black, 8 you have already considered. So how many are remaining? 12 are remaining. Out of total 10 red shirts, 5 you have already filled. So how many are remaining? 5 are remaining. Out of total 15 green shoes, 13 you have already considered. So how many green shoes are remaining? 2 green shoes are remaining. Out of 20 black shirts, now you can recheck. Now you can recheck that whether this 12 plus 8 becoming equal to the given number 20. Yes. Now you can recheck that whether this 5 plus 5 becoming equal to total red shirts given 10. Yes. Now you can recheck that. Now you can recheck that this 8 plus 5 plus 2, 15 becoming equal to the given total number of green shoes. Yes. Yes, yes, yes. So just count everything other than these 3. Just count everything other than these 3 areas. Other than these 3 areas, whatever is remaining, count that everything.
One is 0.36, sir.
0.36. Okay, I calculated only the bracket part and written it. So 1 minus 0.64, that becomes 0.36, that becomes 36%. So I'm interested only in this area in which none of them belongs. How much will be this? 12 plus 8 plus 2 plus 5 plus 5. Subtract from 50. Subtract from 50. 12 plus 8 plus 2 plus 2 plus 5 plus 5. 12 plus 8 plus 2 plus 5 plus 5. And you are going to get 5 + 10 to 12, 12 20, 20 12. But this, is there any mistake we are committing? After learning probability from you, all the probability problems in APTI and maths in GATE exam became a cakewalk. Ramanujan. On a side note, your name itself is the name of the most wonderful mathematician of previous many centuries, most wonderful, most mysterious mathematician. No one can visualize the concepts. Of course, probability is something that 90% teachers don't even understand. I mean, they have algorithmic way and they can, just solve each and every they can solve each and every problem. I don't say they will not be able to solve each and every problem, but there is no systematic way to attack probability. The whole topic is rarely systematically attacked. While topics like differential equations are mostly, in most of the resources, they are attacked very systematically. Type 1, type 2, type 3, type 4, like that. Topics like calculus are also having very systematically divided types of problems and types of questions. But topic like probability, topic like complex analysis, they are really not addressed very well. So have we calculated everything in a neat manner? 20 plus 10 plus 15 minus 5 minus 8. This was actually 32 upon 50. Yes, 0.64. Perfect. So are we getting exactly the same thing? We are getting 50 minus 32, which is 18. And then the required probability will become 18 upon 50. 18 upon 50 is how much? 0.36. Congratulations, you get exactly the same result. Now, in this problem, even though we considered 3 events, even though we considered additional law of probability with 3 sets, we still have not considered all the 3 sets having any common area. We still have not considered all the 3 sets having any common area. But sometimes we might encounter such problems where all 3 sets, look, black and green have common area, red and green have common area, but there is no common area between all 3 of them. Because a person wearing black shirt cannot wear red shirt. But sometimes we might encounter such problems where all 3 sets will have the common area. So as a 10th problem, let's say we go to a classroom. We go to a classroom and conduct a survey. And ask people which one is your favorite subject. It's a class of mechanical engineers. Which one is your favorite subject? A classroom of 60 students. A classroom of 60 students, and we go and ask favorite subject. When we ask favorite subject, we have 20 respondents saying 20 students saying SOM is my favorite subject. 30 students saying 30 students saying FM is my favorite subject. And there are 30 students saying 30 students saying thermodynamics is my favorite subject. Thermodynamics is my favorite subject. I gave them only 3 options, by the way. SOM, FM. No, actually, let's not make it like restricted. I don't give them any option. SOM, 20 students like SOM, 30 students like FM, 30 students like thermodynamics, 30 students like thermodynamics. And my dear friends, there are 10 students I observed. There are 10 students that say that none of SOM, FM, and thermodynamics are their favorite. Basically, some other subject. 10 students have neither SOM nor FM nor thermodynamics in their list of favorite subjects. Let us write it. 20 students have SOM as favorite. 30 students have FM as favorite subject, and 30 students have thermodynamics as favorite subject. Ten students have none of SOM, FM, and thermodynamics as favorite. Fifteen students have SOM plus FM, both as favorite. 10 students have FM plus thermodynamics, both as favorite. And 8 students have SOM plus thermodynamics as favorite. What is the probability of a student having all 3 as favorite? After learning fluid mechanics and thermodynamics from you, it's a difficult choice between 2. That's why I have written equal for FM and thermodynamics. 30 FM favorite, 30 thermodynamics favorite. There is a close fight. So now I'm asking them of their favorite subject. That what's your favorite subject? Please tell me. I'm asking them, what's your favorite subject? And 20 students have SOM as favorite. 30 students have FM as favorite. 30 have thermodynamics as favorite. 10 students have none of them as favorite. 15 have SOM plus FM as favorite subject. 10 have FM plus thermodynamics as favorite subject. 8 have SOM plus thermodynamics as favorite subject. I want to know that what is the probability of a student having all of them as favorite? SOM, FM, and thermodynamics, all of them as favorite. What is the probability of a student having all SOM, FM, and thermodynamics as favorite subjects, what is the probability that a student has all of them? Maybe if I have made some infeasibility while dictating these numbers, I might change some of these numbers. A warning here that since I immediately formulated a problem here right in front of your eyes, so maybe the numbers make some infeasible arrangement. If the numbers make some infeasible arrangement, I will change one or two numbers here. Solving this problem would be much easy task using a Venn diagram. So if I use a Venn diagram, it will be much an easier task. Out of 60 students in the class, some of them have SOM as favorite, some of them has FM as favorite, and some of them has thermodynamics as favorite. My dear friends, I need to find out the common area between all three of them. I need to find out the common area between all three of them. Now, out of SOM and FM, total common students are 15. So if X have been kept here, what value should I put in this remaining area? Tell me. Out of SOM and FM, 15
15 minus
students
X.
have 15 minus X. Exactly. So this one is going to become 15 minus X. I need to make a bigger Venn diagram. So let's make it a bigger Venn diagram. First of all, I'm going to solve it using Venn diagram, and later on I will describe using analytical approach also. Don't worry. So SOM is there, FM is there, and I need to find out the common between all SOM, FM, and thermodynamics. SOM, FM, thermodynamics common to all of them. Okay. Let's say this is I'm interested. SOM, FM, thermodynamics. I want to satisfy all of them. I assume that let's say X students are doing this. Now SOM and FM common number of students were 15. So how many students are going to occupy this area? 15 minus X. Now, my dear friends, thermodynamics and FM, thermodynamics and FM, how many common students are there? Thermodynamics and FM, how many common students are there? 10 common students are there. So X I have already considered. Then how many I'm going to put in this area? FM and thermodynamics total 10 students like both FM and thermodynamics, and out of FM thermodynamics common area, I already put X here. Then in the
10
remaining
minus
area,
X.
I'm going to put 10 minus X exactly. SOM and thermodynamics. SOM and thermodynamics. 8 people are having SOM and thermodynamics both. SOM and thermodynamics common area will have 8. And I have already put X in the central area. So what number am I going to put in this remaining area? In this remaining area, I'm going to put 8 minus X. In this remaining area, I'm going to put 8 minus X. This becomes 8 minus X. Okay. Now this 15 minus X and 8 minus X. Out of 20 students of once again, 50 have SOM and FM both, and 8 have SOM and TD both. So 15 plus 8 becomes 23. I told some infeasible things I might have taken, so I will change the numbers. SOM must be greater than 20. Let's say 28. So out of 28 students of SOM, I have already considered, out of 28 students of SOM, I have already considered 15 minus X, and 8 minus X. In the remaining area, how many I'm going to keep? How many I'm going to fill in the remaining area?
5 plus x.
No, 28 is the total sum. And out of 28 of total sum, I have already filled 15 minus x, x and 8 minus x. So how many do I fill in the remaining area of sum? This is the remaining area of sum. That is exclusively liking sum only. No sum plus FM, no sum plus thermodynamics, no sum plus FM plus thermodynamics. People who exclusively like sum only, they are going to become 28 minus x minus 15 minus x minus 15 minus x minus 8 minus x. Similarly, now you tell me, how many am I going to put in this remaining area of exclusive FM as favorite? No FM plus SOM, no FM plus thermodynamics, no FM plus SOM plus thermodynamics. Total students liking FM is 30. And I have already considered 15 minus x, x and 10 minus x out of that 30. Out of that 30, I have already considered 15 minus x, 10 minus x and x. So how many are we left with out of those total 30 people liking FM? Total 30 people liking FM. I already considered X people in the central area. I already considered 15 minus X people with SOM, and I already considered 10 minus X people with thermodynamics. Now, one last final thing. One last final thing. How many people are having thermodynamics alone, only thermodynamics as favorite? Total thermodynamics is 30. Total 30 people are having thermodynamics as favorite. Total 30 people are having thermodynamics as favorite. So if total 30 people are having thermodynamics as favorite, I already considered x, I already considered 8 minus x, I already considered 10 minus x. I already considered 10 minus x. Now, the sum of all these entries will be what? The sum of all these entries, just to be on safe side, I'm taking the total number of students, not 60, but 90. Let's say total number of students are 90. Now you tell me, sum of all these entries must be equated to what?
All SOM, FM and DOM as favorite.
No. That's not what I'm asking.
So you need
Sum of all these entries, all these yellow, purple, green, blue, orange, all these entries. The sum of all these entries should be equated to 80. Why 80? Because out of 90 total number of students, it's given that 10 don't like any of them. It's given that 10 don't like any of them. Out of 90 total number of students, it's given that 10 don't like any of them. So 10 is this outside area. 10 is this outside area. Okay? This outside area, my dear friends, is 10. And if this outside area is given as 10, then inside these circles, we must have 80 students represented. Inside these three circles, we must have 80 students represented. So I'm going to just equate that total count equal to 80. So 28 minus x minus 15 plus x minus 15 plus x minus 8 plus x. This area covered already. Next, 15 minus x. This area covered again. Next, X, this area covered. Next, 8 minus X, this area covered. And next, 10 minus X, this area covered. Next, FM exclusive पे जाओ 30 minus X minus 15 bracket open minus 10 bracket open. Now last blue entries. The blue entries are 30 minus X, 30 minus X plus, sorry, minus 8 plus X, minus 8 plus X, and minus 10 plus X. This must be equated to 90 or what? This total
Sir,
number
80.
must be equated to 80. 80. Why 80? Because it's given that 10 students have none of SOM, FM, and thermodynamics as favorite. 10 students have none of SOM, FM, and thermodynamics as favorite. So now we are going to have this X getting cancelled and 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 this X getting cancelled. This 8 getting cancelled, submarine. This 15 getting cancelled and this 10 getting cancelled and that's it. Yes. So I'm left with 28 plus X plus 30 minus 15 plus 30 minus 8 minus 10 is equal to 80. 30, 15, 28, yes. Next is X, yes. Next is plus 30, yes. Next is minus 15, yes. Next is plus 30 again, yes. Next is minus 8 again, yes. Next is minus 10. Perfect. So I have made no mistake here. So I am going to get X value as how much? X value. Fingers crossed. I hope that total 90 is resulting into some. Sir, do you eat lesson save? Please reply. You want to send some to my address? Yes, I do, but since I'm on Navratra fast, so of course after Navratra will be over, then I will be able to consume it. So 28 plus 30 minus 15 plus 30 minus 8 minus 10 and 80 minus answer is this much, 25. Now that's not a very feasible result. Yes. How about taking total number of students as 28 plus 30 minus 15 plus 30 minus 8 minus 10. How about taking total number of students as 67? I'm changing total number of students once again, not 90, but 67. Just one little change. Other values I'm not changing. So out of 67, 10 have none of them as favorite. So I equate this to 57. 57 minus 55. There are two people or two students having all three of them as favorite. So probability will become how much? Probability of a person having SOM also as favorite, FM also as favorite, and thermodynamics also as favorite is 2 upon total number of students, that is 67. That is 67. This is 2.98%. 2.98%. Cool. So we can solve these kind of problems using Venn diagram, any such problem. Of course, since I'm formulating the problem without any pre-planning, so numbers feasibility will have to change later. I changed nothing but that 67 only. Out of initially, in fact, I took correct number. I mean, close to correct number. Initially, I took 60 students and I have just made that 60. I have just modified that 60 as 67. Okay. So using Venn diagram, these problems are going to become much simpler, but otherwise, if you try to solve this problem using analytical approach, this is of course going to take a little brainstorming, little thinking, but we will solve it using analytical approach also. Let's solve it using analytical approach also. Before I go ahead and solve it using analytical approach, I just want to very quickly recapitulate entire solution. So let me very quickly tell you that how exactly we attacked this whole problem. Let us very quickly recapitulate how exactly we attacked this whole problem. This given problem is that there is a class of mechanical engineers, total number of students are 67. Total number of students are 67. 28 students have SOM as favorite, 30 students have FM as favorite, 30 students have thermodynamics as favorite. 10 students have none of SOM, FM, and thermodynamics as favorite. 15 have SOM and FM both as favorite. 10 have FM and thermodynamics both as favorite. 8 have SOM and thermodynamics both as favorite. Now, question is asking me that what is the probability of a student having all three? What is the probability of a student having all three, SOM, FM, thermodynamics, all three as favorite? What is the probability that SOM is also favorite, FM is also favorite, thermodynamics, all three are my favorite? Now you go to interview and then the examiner is asking, tell me, Mr. Changu, what are your favorite subjects? So some people say, sir, SOM and FM. Some people say SOM and thermodynamics. Some people say FM and thermodynamics. Some people who think, which is a wrong step usually, who think that they have prepared all three subjects, they say, sir, SOM, FM, and thermodynamics. In an interview, whenever you go, don't say the name of three subjects. Just say two most commanding subjects, okay? Every interview is always going to start with this basic question that what are your favorite subjects? So why to give more chances of grilling? Huh? You should not give more chances of grilling. So how we approached this particular problem? This particular problem we approached like total 67 students are there. And then there are people belonging to FM alone. There are people belonging to SOM alone, FM alone, and there are people belonging to thermodynamics alone. Now, I'm interested in the common area of all three. Always start at the center, even if it is unknown. Remember the rule, always start at the centralmost area, even if that centralmost area is unknown. Even if that centralmost area is unknown, even then start at the centralmost area. Okay. Now, out of SOM and fluid mechanics, how many of them like both 15. So out of 15, I already placed X here. So in the remaining part, I'm going to place 15 minus X. Similarly, thermodynamics plus FM, there are 10 students. Thermodynamics plus FM, there are 10 students. And I placed thermodynamics plus FM, there are 10 students. And I placed X already. If I placed X already in the remaining, the FM plus thermodynamics, I have 10 minus X. Now, SOM plus thermodynamics. SOM plus thermodynamics, there are 8 people. There are 8 people having SOM plus thermodynamics both. I already considered X. I already considered X. So, how many are common people remaining now? 8 minus X. Out of 28 people, out of 28 total people representing SOM, 15 minus X and 8 minus X have already been considered. So how many are remaining? 28 minus these three things. 28 minus these three things. Now, I know how many people in terms of X, I know how many people are exclusively liking SOM alone. Total 30 people like FM, but out of that, I considered 15 minus X, I considered X, I considered 10 minus X. So out of 30 total people having fluid mechanics as their favorite, I already considered 15 minus X people, I already considered X people, I already considered 10 minus X people. Out of 30 people having thermodynamics as their favorite, I already considered X, I already considered 8 minus X, and I already considered 10 minus X. But since it is given that 10 students don't have any of them as favorite, 10 students don't have any of them as favorite. So where is that 10 represented in this Venn diagram? In this Venn diagram, where is that 10 represented, people? That 10 is represented outside of SOM, FM, and thermodynamics. The 10 is represented outside of this SOM, FM, and thermodynamics. 10 is what? 10 is the number of people who like neither SOM, nor FM, nor thermodynamics. Probably they never learned these subjects in an unmatchable manner. So SOM, FM, and thermodynamics people, there are 10 people who don't like any of them. If any non-unmatchable student get this type of problem, he'll run away. Sure. That's 67% chances are that if a non-unmatchable student will get this kind of problem, he will run away. Because it's really a puzzling problem. Now we are going to say that if this 10 is there, and just keep adding all the areas, that's it. Now your job is easy. 28 minus X minus 15 plus X minus 8 plus X plus next area 15 minus X plus next common area X plus next SOM TD common area 8 minus X plus next FM exclusive area. FM exclusive area is 13 minus 15 plus X minus 10 plus X minus 10 plus X plus FM thermodynamics common area, FM thermodynamics common area plus finally thermodynamics exclusive area. Thermodynamics exclusive area is 30 minus X minus 8 plus X minus 10 plus X and this becomes total equal to 57. Many terms are going to get cancelled. For example, this x gets cancelled, 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 and this x also gets cancelled. This 15 gets cancelled, this 8 get cancelled, this 10 gets cancelled, and anything else? No. So now we are left with 28. First term is remaining. Next, all of them got cancelled. Next term that is remaining is 30. And then next term that is remaining is minus 15. And the next term that is remaining is 30 again. And the next term that is remaining is minus 8. And then minus 10 plus x is equal to 57. Now I'm going to get x is equal to 2. That means all three common subjects, all three as favorites. There are very rare people. There are very rare number of students who have all three as common, all three as favorites. So final probability becomes 2 upon 67. 2 upon 67. 2 upon 67 is 0.02985. 0.02985, which is 2.985%. 2.985%. Cool. Can we solve this problem without Venn diagram using analytical approach? Yes. Can we solve this problem using analytical approach without using Venn diagram? Yes, we can solve it. How we can solve it using analytical approach? Let's see. So we are now going to solve it without Venn diagram using our earlier analytical approach. In previous problems, previous 3-4 problems, you remember rain and storm wala problem? Rain and storm problem, then dog and cat problem, dog and cat problem, and then party problem, red shirt, black shirt, green shoes, and then favorite subject problem. And all of them we have solved using both analytical approach and also using Venn diagram. Using analytical approach and also using Venn diagram. So can we solve it using analytical approach? Yes. How? That I'm interested in all of them as favorites, but I'm going to begin with this information. I'm going to begin with this information. No SOM, no FM, no thermodynamics. No SOM and no FM and no thermodynamics. No SOM and no FM and no thermodynamics. I'm going to begin with this. No SOM. And this number is given to me, by the way. This number is given to me. This number is given as 10. No SOM, no FM, no thermodynamics. This number is actually given to me. 10 people have no SOM, no FM, no thermodynamics as favorite. But using De Morgan's law, I can write, you remember De Morgan's law? De Morgan's law says that no matter how many events are there, probability of complement of unions is equal to probability of intersection of complements. So if you have SOM complement intersection, FM complement intersection, thermodynamics complement, that number is given to you as 10. I can write using De Morgan's law. Using De Morgan's law, I can write it as SOM union FM union thermodynamics whole complement. But then you know that probability of probability of complement of any event will always be equal to 1 minus probability of 1 minus probability of that event. Probability of complement of any event is equal to 1 minus probability of that event. So probability of hat complement will be equal to 1 minus probability of hat. Probability of brick complement will be equal to probability of 1 minus probability of brick. So if somebody understands, tell me. This can be proved using which axiom of probability?
Second axiom, sir.
Second axiom. That's it. Actually, second plus third. If there is one event defined as hat, then there is hat and there is hat complement, but probability of total sample space is 1, but total sample space is union of hat and hat complement is equal to 1. Since hat and hat complement cannot occur simultaneously, they become mutually exclusive events. So now I use third axiom. So using third axiom, I write union is equal to sum, and that becomes 1 minus probability of hats. Using second axiom plus third axiom, you can prove that probability of complement of anything will be equal to probability 1 minus probability of that. Now, using additional law of probability, this thing can be expanded as probability of SOM as favorite plus probability of FM as favorite plus probability of thermodynamics as favorite minus probability of SOM FM together as favorite minus probability of FM thermodynamics together as favorite minus probability of thermodynamics and SOM together as favorite plus last one, probability of SOM, FM, thermodynamics, all three as favorite. My dear friends, the left hand side is already known to me, 10 upon 67. In the right hand side, I'm going to have probability of SOM equal to 28 upon 67. Probability of FM is equal to 30 upon 67. Probability of thermodynamics as 30 upon 67. Probability of SOM plus FM as favorites 15 upon 67. Probability of FM and thermodynamics as favorite 10 upon 67. 10 upon 67. Probability of thermodynamics and SOM as favorite 8 upon 67. 8 upon 67. Last one I want to know. Last one I want to know. This is the main unknown for us. SOM, FM, thermodynamics, all three as favorite. There is only one unknown in the problem now. Go ahead and solve for it. 28 plus 30 minus 15 minus 10 minus 8 upon 67 and 1 minus answer minus 10 upon 67, 0.0298, exactly the same result. $0.02985. So far, we have been considering a single sample space. So far, all the problems that we have solved, we have been considering a single sample space. 10th problem, we considered a classroom, a single sample space. 9th problem, we considered a party, 50 people, a single sample space. Eighth problem, we considered a society of how many households? 150 households, 150 families, society of 150 families, party of 50 persons. There is a party going on, party, and there is a classroom of 67 students. There is a classroom of 67 students and society of 150 families. Society of 150 families. Problem number 7, there was rain and storm. Again, there was rain and storm that we solved yesterday. Again, a single sample space. Problem number 6, again, a single sample space. We rolled 2 die. Actually, it's not a single sample space, but we considered it as a single sample space. So there are 36 possibilities, and we considered it as a single sample space in problem number 6, 1, 1 to 1, 1 to 6, 6, 36 possibilities. Even problem number 5 was rolling 2 dice only. Even problem number 5 was rolling 2 dice only. So again, 36 possibilities from both die getting 1 and 1 to both die getting 6 and 6. Now is the turn that we say roll a die and draw a card. Now we say ask a student favorite subject and ask a family. Having pet or not. When we combined multiple sample spaces, it becomes a compound random experiment. When we combine multiple sample spaces, it becomes a compound random experiment. And this interesting probability problem of solving compound random experiment or compound sample space, such one is known as compound experiment. Such one is known as compound experiment, where you can't define a single sample space. You will have to asking students of their favorite subject is totally a different phenomenon, and asking a family whether that family has dog or cat as pet is totally a different phenomenon. Rolling a die has totally a different sample space, and drawing a card has totally a different sample space. Such experiments are known by the name compound experiments. And tomorrow, in the next class, we are going to deal with these kind of compound experiments where we'll have multiple sample spaces considered together. And we would like to know whether certain event from one sample space and certain event from another sample space are happening simultaneously. We would like to know that if a roll die and draw a card, then a 6 on die and a king from cards, are they happening simultaneously? When we ask a student a favorite subject and we ask a family whether that family has dog or cat as pet, then what is the probability of a student having some as favorite, and what is the probability of that family having dog as pet simultaneously? We would be interested in co-occurrence of event A defined on one sample space and event B defined on another sample space. This is going to be one of the most interesting problems of probability compound experiments that we do in the next class. Thank you so very much, people.
Sir,
Hmm.
here can we consider the sample space as finite sample space or what's it?
Which one?
Compound experiments.
That we will study tomorrow. We'll see.
Okay, sir.
So don't worry, that we'll study tomorrow. Compound experiments are interesting things. We'll see what can be done with them. All right, people, let's call it a day. And tomorrow we'll do compound experiments and also Bayes theorem. This is what is the power of consistency. Gradually, slowly, but we are on the verge of completing probability in the next couple of classes. I mean, only probability, then probability distributions. Next chapter will start. Okay, people. Bye-bye then.
Sir, tomorrow also same
Yes.
timing, sir.
Tomorrow also same time.
Okay, sir.
11 to 1, we will have mechanics. We'll finish friction. And then a little longer class of probability. I will try to finish probability chapter tomorrow itself, like including Bayes theorem. So that when we start next week from Wednesday, then we can start with second chapter, probability distributions.
And mechanics virtual work will be there, sir.
Mechanics, sorry, ask it again.
Virtual work, sir. Static part.
Virtual work will do. Virtual work will do. I mean, tomorrow we'll finish friction first, and then we'll do virtual work. I have a target of completing probability plus mechanics both by next Sunday.
Okay, sir.
All right, people. Thank you.